So welcome. Today we're going to talk about the Mamba paper, and the plan is I'm going to present a little bit of an outline, but I'm really going to lean on uh, some videos to talk about Mamba and to talk about some of the state space models S4 before that. So really, I'm just going to be linking and heavily leaning on the work of some great YouTubers. So let me share my screen and bring up the slides. Okay, so this paper, linear time sequence modeling with selective state spaces, by Albert Gu and Tree Dow. They're both Stanford people, but I think Tree's now at Princeton. Um, I thought I would read the abstract. I apologize, it's a little bit long, but I thought that the abstract does do a really good job of characterizing why they worked on this model. Okay, so it says foundation models now powering most of the exciting applications in deep learning are almost universally based on the transformer architecture and its core attention module. Many subquadratic time architectures, so full attention is quadratic. People have tried building, performer, linformer, whatever, sparse this, RKV, WV, whatever, these subquadratic, faster than quadratic architectures, such as linear attention, gated convolution, and recurrent models, and structured state space models, have been developed to address transformers' computational inefficiency on long sequences, but they have not performed as well as attention on important modalities such as language. We identified that a key weakness of such models is their inability to perform content-based reasoning and make several improvements. So content-based reasoning means when you see this token, when you see this word, you're going to do something different than if you had seen a different word for the language case. Make several points. First, simply letting the SSM parameters be functions of the input addresses their weakness with discrete modalities. So language is discrete. It's like, token, token, token versus like speech is more time continuous. Allowing the model to selectively propagate or forget information along the sequence length dimension, depending on the current token. Second, even though this change prevents the use of efficient convolutions, we designed a hardware-aware parallel algorithm in recurrent mode. We integrate these selective SSMs into a simplified end-to-end neural network architecture without attention or even MLP blocks. We call this Mamba. Mamba enjoys fast inference, 5 times higher throughput than transformers, and linear scaling in sequence length. And its performance improves on real data up to million length sequences. They didn't do language million length, but they did like DNA or whatever. As a general sequence model backbone, Mamba achieves state-of-the-art performance across several modalities such as language, audio, and genomics. On language modeling, our Mamba 3 billion model outperforms transformers of the same size and matches transformers twice its size, both in pre-training and downstream evaluation. So that's not quite to the point of what we call a large language model LLM, right? Those tend to start around like 7 billion, but you're just on the verge of that. And they were able to match performance of a transformer trained from scratch on the same data as Mamba using the best recipes we know how to train transformers. So that's very impressive. Okay, so the overview of this is that Albert Gu worked on state space models. He worked on and developed S4, okay? And so now he's building on this and creating this selective state space model that allows some of the matrix trainable parameters to depend on the inputs, as it said in the abstract. Okay, this gives it more flexibility, more power, but this breaks the mathematical equivalence to convolution, and so he probably worked for a while to see if he could come up with some new mathematical trick to use convolutions and failed. And so then said, well, what can I do? And ultimately said, if I can't actually turn it into something that's inherently fast, what if I just program it in CUDA really well and make it run really fast? And that's what they did. So this new state space model is S4 plus. It does this parallel scan thing, and it does this selectivity thing. So he calls it S6. It's got 2 more S's. And you don't just use a state space model like all by itself. So it's in a block. It includes an MLP. It's a little bit different from H3. It's a little bit different from some of the other ones, but we're not going to cover it. But the ablations showed some modest improvements, and those may have been needed in order to claim, hey, we beat the transformer, we're state of the art. But they were pretty minor. So the block isn't that important. The really important thing is the S6 at the heart of it. So moderate sized experiments show the ability to handle, he said, very long sequences, and their 2.8 billion parameter model matched, LLMs with transformers. So bottom line is there's a lot of buzz. People are anxious for somebody, either Albert Gu or people who have now read the Mamba paper, to build 7 billion, 13 billion, 11 billion, or bigger, 3070, right? Models and see if they actually, compete with Llama 2, Mistral, our sort of, favorite current LLMs.
Hey Ted, I'm not super familiar with state space models. Are these like edge transition type models, or are they?
Yeah, so we're going to get into it.
Okay, all right, cool. Sorry.
So
Just
yes,
making sure that if I'm missing the basics, I'm gonna doze off here pretty quickly.
Yep.
I also had two, and defer them to later in the content if that makes sense. But one was you said that the training was done based on best practices. So we've seen a lot of improvement in smaller models just by using different training methods, right? So you're saying their comparison is against well-trained transformers.
Yeah, so they
Models.
they read the Palm paper and the Llama 2 paper, and they took every trick that they
Right.
knew had been published and tried to train the transformer that way.
Great.
The same number of parameters as Mamba, and that's what they ultimately include in the paper is their comparison to
Great. Okay.
as best as they could train.
And great. And then the second one, and again, just defer, it makes sense, but longer sequences give more context. They're better for being able to provide plug in some of the retrieval augmentation, et cetera. But we've also heard that long sequences kind of make noise. The performance degrades a little as the sequence gets long. And I'm just wondering if they address that at all or not.
It's not addressed. They address some other problems that are typical long sequence problems, okay? But they really only do like 8K sequence length language models, comparing basically an 8K transformer to an 8K Mamba.
Okay.
So
Thanks.
they don't really, get there yet. I think if Mamba continues to scale in quality as it gets bigger on language, people are pretty optimistic because it does well in these other things that are super long, but they didn't explicitly test language super long.
Okay, that makes sense.
Just to add on Hugging Face, Mamba-based attention replacements have started coming up. I do not recall exactly how they compare, but 2.8 billion parameters. And I think overall it is doing very good, but I don't recall the benchmark numbers. But within 2 weeks of its release, right around NeurIPS 2 weeks ago, it has started making into some models out there where people are replacing attention, just the attention part of it, with Mamba and seeing definitely good results, but again, from a very, very smaller model compared to 7 or 14 billion parameters models.
Cool. There's a question in the chat. I don't know the answer. Are these structured state space models the same things that people talk about in econometrics? I don't know. We are going to actually spend most of our time with the background on what these state space models are today. We might get a little bit into Mamba, but I think mostly we're just going to be talking about that today. So we'll get into it, and if you know, then you'll be able to see whether or not these are. There's a lot of different kinds of these recurrent models. Dave, your hand's raised. Is that from before, or did you want to add something else?
Yeah, Ted, this is me. So these are the state space models from 50s and 60s, mostly in the control theory space. So both Tree Dow and Albert Gu, one of the couple of things that they have added to the space transformers, and in this case with S4, is as mentioned in this third bullet here, replace the GPU hardware optimized algorithm. So Tree Dow's one of his famous works is Flash Attention, which was leveraging that in the GPU hardware optimized algorithms, and that derives, if you would ask him or listen to some of his videos, it's like databases 101, not even sharding or anything, just optimizing the I/O, and in this case, the I/O for GPUs. And Albert Gu, if you listen to his videos, it would be like control theory and electrical engineering 101. And I know we have some people from electrical engineering background here. They can maybe relate to that. So just leveraging the very basic control theory SSM models. But yes, Ted, when you go into that, we'll know more.
If I remember right, Deb, and one of the, just kind of building off of that, from if this is the same thing as control theory, that if it's non-deterministic, it explodes into n by n by n by steps to the power of steps. If it is deterministic, it's overly simplistic, and that'd be kind of the overall architect, like summary of that state space model that I recall. Is that the right way to kind of condense the history?
I think they do talk about how they manage the explosion, but maybe not in this video.
If I were just to summarize it was either the deterministic one, which is where you move from this state space to this state space, and it was just very, very rigid, or it immediately exploded. Those are kind of the two choices you had with that representation model.
Yeah, so we're going to get into it, but basically,
okay, all right, sorry.
If you're familiar with, because the video does not cover this, if you're familiar with like a Markov chain, okay, right? You've got a certain number of states, and then from every state, you can either have deterministic, where you go to whatever the next state, or you can have it be stochastic, where like, you flip a coin and you randomly choose based on probabilities what your next state is going to be, okay? So that's a very simple model where it's just based on what state you're in, and then you're going to transition to the next state, okay? In this case, what we're going to do is we're going to have a linear function for the output that's based on the input and our state, but we're going to have something a little bit more advanced. We're going to have a linear function based on the first derivative instead of on just the state, okay? So, so for our hidden representation, we're really looking at not just h, but dh dt. And so you'll see that's what today is all about talking about. So you don't have to get your questions answered now. That's what Albert is actually going to explain in the video that you had linked, David. All right. So the first video we're going to show, we're going to pause at the 6-minute mark, and he's just going to do a little history over what kinds of things have people done to try to deal with really long sequences, okay? Because long sequences are hard, and if you do something like an RNN has a fixed width hidden state, okay? If you do just a simple RNN, then what happens is you're very compact and you're very computationally efficient, but there's only so much you can pack into this. So if you say, okay, I'm going to build an RNN with a really big hidden state, 8,000. Well, okay, what happens when your sequence length is 80,000, right? Well, then I'll make an RNN with a hidden state of 80,000. Well, then what happens when you get to 800,000? You ultimately just can only pack so much into this hidden state, right? Transformers completely blow that problem because they don't store hidden state at all. They just simply say, at any moment in time, you can directly look at all of the historical entries, but it becomes this problem with memory and compute because as the sequence gets really long, it's quadratic in terms of like storage and compute. And there's some inefficiencies with like flash attention and whatnot. But basically, you run into this problem that if you want to sequence like 800,000, how are you going to compare your current thing to all 799,000 previous things, in parallel, right? So is there actually something that performs as well as a transformer without doing the full comparison? It has to have some kind of state and it has to have something. And so that's the holy grail that people are looking at. And so we're going to see these models, okay? Legendre memory units, and then Hippo. Then we're going to see these state space models ending with S4. And so that's going to take us 6 minutes.
Mamba, linear time sequence modeling with selective state spaces, appeared on arXiv. It is causing some excitement, partly because it shows strong empirical results,
We now have Grammarly Business.
partly because it has an interesting design, and partly because Mamba is a great name. In this video, I'll give a high-level summary of the paper. To understand the motivation for this work, it's helpful to go back in time to the distant memories of 2020, and in particular, the long-range arena, a benchmark for efficient transformers. The starting premise was that transformers do not scale very well to long sequence lengths, largely because of quadratic self-attention complexity. Given the proliferation of efficient alternatives to transformers that were emerging at the time, this work proposed a benchmark specifically focused on evaluating model quality under long context scenarios. There were tasks like long list ops, where the model is given an input consisting of a long list of nested operators and needs to calculate an answer, and fun tasks like Pathfinder, where the model gets a flattened image that looks like this and needs to determine whether the two circles can be joined. This is a positive example because they can. This is a negative example because they cannot. Broadly, they found that if you wanted to maintain performance, encapsulated here in this LRA score, it's quite hard to do much better than the vanilla transformer. Independently, and a little earlier, a creative approach to tackling the long-range dependency problem was introduced in this work on Legendre memory units, in the context of recurrent neural networks. As a refresher, Legendre polynomials are these beautiful creatures. You can construct them by making a sequence of polynomials that are orthogonal to each other. By projecting values onto a basis of these polynomials, you can efficiently store a history of the inputs to your system. That's the key idea in this funky looking equation. You can reconstruct the input u by reassembling it from the components of the memory vector, denoted here by m. This idea can then be baked into a layer where the memory block is implemented with simple linear operations. Building on that idea and others, Hippo, recurrent memory with optimal polynomial projections, had the insight that we can phrase memory as a technical problem of online function approximation, where a function is summarized by storing its optimal coefficients in terms of some basis functions. Using this insight, the authors constructed a simple model based on Legendre polynomials that worked well on tasks like permuted MNIST, outperforming other sequence model-based baselines like LSTM and dilated RNN. This was followed by the work combining recurrent, convolutional, and continuous time models with linear state space layers, which proposed a unifying framework for sequence modeling based on a standard state space representation. This work showed how, starting from an implicit continuous time state space model, you could discretize to produce a system that can be interpreted as a recurrent network with the benefit of efficient inference, or as a convolutional model, which benefits from parallelizable training. Unfortunately, a naive implementation of these models requires a massive amount of memory. In fact, for reasonably sized models, such as when the state dimension is 256, the linear state space layer uses orders of magnitude more memory than comparably sized RNNs or CNNs. That brings us to the S4 model, introduced in efficiently modeling long sequences with structured state spaces. What we'd really like to be able to do is use the convolutional interpretation we've just seen to efficiently train our state space model. Now, if we want to train state space models using the convolutional representation, we can do a little bit of unrolling and a little bit of vectorization to get this L-dimensional kernel, where L is the sequence length. The scary part here is this a raised to the power of I term. Harking back to your linear algebra classes, as soon as you see this, you may feel a strong and appropriate urge to try to diagonalize A. The authors discuss diagonalization. Unfortunately, it cannot be used directly for the Hippo matrix due to numerical issues. Specifically, it has entries exponentially large in the state size. However, we can address the Hippo matrix with an adjustment. The authors note that although the Hippo matrix is not normal, it can be decomposed as the sum of a normal and low-rank matrix. Even this is still not useful by itself. An additional 3 new techniques are needed. First, instead of computing the kernel k-bar directly, they instead compute its spectrum, then determine k-bar by applying an inverse FFT. Next, we use everyone's favorite low-rank trick, the Woodbury identity. That lets us perform an efficient matrix update. Third, it is shown that the diagonal matrix case is equivalent to the computation of a Cauchy kernel, a well-studied problem with stable near-linear algorithms. All of this comes together in Theorem 3. It says that given any step size delta, computing the state space model convolution filter k-bar can be reduced to 4 Cauchy multiplies, requiring only big O of n plus L operations, ignoring logarithmic factors, and big O of n plus L space, where again, L is the sequence length and n is the state size. Empirically, the proposed S4 architecture does very well on the long-range arena, even doing well on the path X task, where the model must determine if 2 points are connected on a fairly large image. This task is not too hard when the input is arranged as an image, but it's pretty difficult when it's a flattened sequence, as evidenced by the fact that many other models fail on this task. If you'd like to gain some intuition for how S4 works, I highly recommend The Annotated S4 by Sasha Rush and Sid Karamchetty. Just as with the legendary Annotated Transformer blog post back in 2018, the Annotated S4 takes you step by step through the paper and provides snippets of code that implement the mathematics. It also includes nice visualizations to help you build intuition for how state space models work. All of this brings us back to Mamba. This work builds on the state space model approach.
All right, so we're going to pause here. So that's a little bit of background in terms of what people have been doing to try to model long sequences. And so then the next thing we want to do is actually get into the state space model stuff. We're not going to get heavy deep into the math, but just more so people sort of understand the intuition. Okay, so I have a video of Albert himself explaining S4, and he goes into some of the background. So he's going to build this up, but where we're going to get to is that you have this continuous time state space representation, okay? So your output is just this simple linear function of your hidden state X and your input U, okay? So this is very simple. This is a standard linear function. Now, because these are multi-dimensional, C is a matrix. It's not just an integer, okay? And D is also a vector. It's not just a single constant, but it is basically still just a linear function. It's just a function on vectors instead of individual reals. Where things get interesting is, I was saying, this top equation is not a linear function on X. It's a linear function on the first derivative of X, dx dt. Okay. They use X instead of H for the hidden state in almost all the state space stuff. I'm not exactly sure why, but if you're used to RNNs, you're probably used to seeing H instead of X. So the idea is that if you take this function, which is operating on continuous data in reals, okay, and you have a delta time step that's, let's say, 1/60th of a second, what you can do is you can just calculate the integral of this from time step t till time step t plus 1/60th, okay? And what you will very quickly see is that you're not going to get just plain linear dynamics because, right, this is a slightly more complicated function and you're integrating over it. So when you do that integral, however, you will get this new constant they call a bar. Okay, I'm not showing it on the slide, but you'll see an equation. Okay, so basically this is this a bar constant times the previous state plus b bar times the input. Okay, so these are not the same a and b above, but basically it's still just two constants. Now you have to do the work of calculating the integrals and everything, but at the end of the day, you will get two new constants. Not so bad. So then the idea is that even though this is supposed to be a continuous thing, you could do inference just like in RNN, where you plug in one input and it pops out an output and updates the hidden state. And you plug in your next input and it pops out an output and updates the hidden state and just keeps running like that. Okay. We know, though, that the big problem with RNNs in machine learning has been that they're really slow to train. Okay. They're sequential, they're not parallelizable, and this back propagation through time, typically when you do it, consumes tons of memory and is slow. So the harder math that, honestly, I read the S4 paper and I could not follow the math. It crushed me, okay? But if I trust the authors, okay, they did the math and they basically said, I can do some things and I can figure out how to create a convolution. It's the same idea as the convolutions in a CNN. In a CNN, you typically have small convolutions, okay? So like you imagine a 3x3 filter, a 5x5 filter, and they're two-dimensional, but in this case, it's gonna be a one-dimensional convolution, okay? Ultimately, the convolution they build here is the length of your entire sequence. So it's not actually going to move across your thing. You're just gonna, I can't remember if you move it or not, but anyway, it's going to be a really giant one that's the same size as the length of your sequence, but nevertheless, you can calculate what this thing is, and because these a bar and b bar or whatever are constants, you can just imagine unrolling your RNN L times whatever your sequence length is, and you do a bunch of math, and then you can ultimately get at this thing. And if these constants are known in advance, then you can unroll it in advance and you can just compute stuff. And that's where in the video he said, but wait, you have this problem of a bar to the, if your sequence length is k, kth power, k minus 1, k minus 2, k, all the way down. And that's even though it is computable in advance in order to save you cost at inference time, it's still a real pain in the neck to compute. But nevertheless, the fact is that what you can do is during training, you treat it like a convolution, because then you get to parallelize and you get to go, bam, I'm going to do this. But during inference time, you treat it like an RNN. You use the middle one, the discretization, and you pop in one input at a time and you pop out one output at a time. That's where we're going with this. Okay, so pictorially, he's going to explain this. All right, but you're going to see that continuous, if the electrical engineers amongst you, the signal people will understand, like, here's your input, okay, and at the top out pops your output, and here is this sort of feedback loop with this A thing operating on the derivative here, and that's why there's this integration happening in the middle. If you are familiar with RNNs, this diagram will look familiar. You send in an input, it calculates a new state. You send in another input, it calculates a new state. And at each step, it just pops out an output. And then this is like one giant convolution K-bar that's operating on your entire sequence. So the cool thing is not just like conceptually we have these, but that like this actual whatever block has the properties of all three of these simultaneously. So you can choose to work with it in whichever way you want. So what people choose to do is they want to emulate the continuous time dynamics. They run convolutions at training and they run recurrent at inference. So he will probably explain it a little more technically, a little better than me, but I just wanted to give you guys the preview of what we're going to be talking about. Question?
Yeah, quick question. If you can go back one slide. The line equation number 4, I just wanted to see, is that correct? I see that it's xt minus 1, but it's b bar ut. Not, I guess instinctively I was thinking that would be ut minus 1. Is that correct?
It's
As it is?
from the paper. Papers do have
Then it's gotta be
typos,
right.
but
Okay.
I think it's
Okay.
correct.
Okay.
So it is UT.
I think it is correct, because if you go to the next slide, and kind of combine it in, if you look at the recurrent, the UT is the input of that discretized step.
Like down
So
here.
it's that, yeah, that's right. So if you go back to the equation, what you're essentially saying is, in equation 4, and good God, I hope I got this right, but I'm going to try, which is that xt, which is essentially the feedback from this step. Xt is the result of the prior step's feedback, xt minus 1, times some derivative of a, which is a bar, and it's a mathematically computable derivative of a, where a was the continuous version of this, and this is now the discretized version of it, plus bu times the absolute systems input, which is ut, which is this current input to the whole system.
Yes, I think it's
That
exactly
allows
what
you
you
to
said,
compute
with one
just the
caveat.
x.
It's a bar is actually the integral of a, not the derivative of a.
Oh, sorry, yeah, so it is derived from a. I didn't know there was actually an integral. Great. Yes,
It's the
and that makes
integral.
sense.
It's the integral of equation 1. So
It's
actually
the integral
gonna
of equation 1 with relation to
A's and
time
B's.
over the period that we've used for discretization.
Exactly. Whatever your time step.
That makes perfect sense. And so you're not computing y though. If you're computing y, then your comment would be kind of spot on, right? It's that you're computing x in that first one. Then the second one you're computing y, which is the actual outcome. When you're computing x, that's effectively the feedback, the a loop on the continuous time diagram on the left there.
Yeah, that's great, Sally, because yeah, you're right. I don't know if you can see my mouse, but in the middle of this diagram, you use a bar to go from xt minus 1 to xt. And then once you have xt, you grab your input. So really it is b bar times your current input. And then you take your current state, and then you can generate your output.
But I will go so far as to say that while Ted did say this is the simplification of it, there is nothing simple about what he just did in the last 2 minutes.
Okay, so this we're going to see, and again, hopefully Albert explains it better than me, more rigorous than me. This is the visual. If this works for some people better, if the equation works for some people better, whichever works for you better, run with that version of it, okay? Okay, and then in this video, he's going to explain these 3 views. He's going to talk about some challenges for deep state space models, okay? Even though mathematically this is all fine, when you try and do it in the real world, you're going to get vanishing gradients, because if you have an A matrix, okay, fine, we did a sequence length of 100, so you have A to the 100th. If you have a sequence length of 1,000,000, you have the A matrix to the 1,000,000th power, and you're supposed to take derivatives back on that, right? And then it's also expensive to compute. So he does not go into the math, so he's not going to kill us on these hippo operators. But S4 uses that, and S4 at the time was showing state-of-the-art results, but wasn't challenging language models for NLP. So that's the
You're
setup.
saying that a number less than 1 to the 1,000,000th power is really big?
A number, anything other than 1 to the 1,000,000th power is going to be numerically a problem for you.
Yes. I mean, that is the fundamental problem with RNNs, right?
Yeah. So I had a teacher, I don't remember what grade, but who was sort of like a big fan of the tell me what you're going to tell me, then tell me what you told me thing. So I'm trying to do that first part, okay? I'm going to tell you what Albert's going to tell you, but then I'm going to let him actually tell you more rigorously than I can. So this is 27 minutes. the entire video before we get to Q&A. And so that will take us to the top of the hour, basically.
Cake in the break room! Cake in the break room! There's cake in the break room.
Video more naturally.
Oops.
So as always, we're going to do a 30-minute talk by Albert, followed by a 30-minute podcast-style discussion where you in the YouTube live chat can post questions, and we'll get those questions across to Albert. You can keep posting those questions during his talk, and we'll aggregate them and get those across. A little bit about the talk today. So Albert's going to be talking to us about modeling long sequences with structured state spaces. And he's going to describe a new model that he's built. He is a PhD student in the Stanford CS department, advised by Chris Ray, and is interested in structured linear algebra and the theoretical properties of sequence models. He's also on the job market, in case there are any folks listening. Take it away, Albert.
Thanks for the introduction, Karan. All right, so as Karan said, in this talk, I'll be introducing a new sequence model. To set the stage first, let me just talk about the types of problems that we hope to solve. So we're going to address long and implicitly continuous sequences as our main motivation. And I'm just going to call these continuous time series. To give some examples, on this slide here are some examples of typical time series data of this nature. On the left is medical time series such as EEG or ECG signals. In the middle is a typical speech waveform. And on the right are energy forecasting signals. So in general, continuous time series are defined by sequence data that's sampled from an underlying continuous signal. This type of data is something that people don't usually think about when talking about sequence models, but it's a very challenging type of data with unique characteristics. So for example, speech data is typically sampled at 16,000 hertz or even higher, which means that for clips of just 1 or a few seconds, the sequences are tens of thousands of samples long, which is already much longer than what deep learning models can typically deal with. So unlike other ML fields like vision, where end-to-end deep learning models perform well, in speech, for example, typically you need to rely on substantial feature engineering and complicated pipelines. So in this talk, we're going to try to address these with using generic deep sequence models. And for the purposes of this talk, I'm defining a sequence model as just a sequence-to-sequence map composed of primitive layers, where concretely each layer should operate on a sequence of inputs that is a sequence with a hidden dimension and output something of the same shape. And to give some examples, up top are some classical families of deep learning models that satisfy this interface. These include continuous time models, recurrent neural networks, convolutional neural networks, and transformers. These families all have different strengths and weaknesses when it comes to modeling sequences. But for continuous time series, like the motivating examples, these first three are more conventional, and I'm going to focus on them first for now. So in a little more detail, we define continuous time models as models that directly try to model the underlying continuous process of data. This allows them to capture the inductive bias of this type of data better and perhaps automatically do things like handle missing data in other applications. Recurrent neural networks, or RNNs, are a natural stateful model where they summarize information they've seen to a hidden state. And so they're better in certain settings, in stateful settings like reinforcement learning, and they can also perform certain autoregressive tasks more efficiently. And convolutional neural networks, or CNNs, are easily parallelizable. So they scale much better and are much easier to train than the others. So every model has clear strengths, but also has clear weaknesses. So for example, continuous time models and RNNs are both slow, and they suffer from what's called the vanishing gradients problem because they're inherently sequential. On the other hand, CNNs don't have this problem because they're kind of more global and parallel, but they do have inherently bounded context, which makes them unable to address long dependencies. So in general, each of these families has strengths and weaknesses and some clear trade-offs. And all of them have something that holds them back for addressing really long sequences, like the types of problems that we're going to be trying to solve. So our first goal in this talk is to see how we can combine the strengths of these families into by using what's called a state space model. This is a little diagram that I'll unpack later about, so the high level is that this model is going to have 3 different representations that can be switched back and forth between each other. And each representation gives it the benefits of one of those 3 paradigms, continuous time, recurrent, or convolutional. All right, so as a little preview of the results, here is a recent benchmark for long-range sequence modeling. It consists of 6 tasks across many different types of data that span from 1,000 to 16,000 length sequences. And for context, usually in sequence modeling, things that are even 1,000 or even like a few hundred steps is often considered long context. So this is extremely long context. And our new model does really well in this benchmark and outperforms every baseline that we're aware of by a substantial margin. Okay, so first, I'll introduce the model and walk through a bit of the mechanical details. So the model is based on the state space model, which is a well-known model in many scientific and engineering fields. It's defined by just these 2 equations. So the way we think about it is that we think of these 2 equations as defining a parameterized function-to-function map. And throughout this talk, I'll use the same notation where U denotes an input, sequence, or function, and Y denotes the output, sequence, or function of our sequence model layer. So here we think of the state space as a map from, it's a parameterized map using parameters A, B, C, D, and it maps some input function U to an output function Y. It's sometimes drawn with this sort of control.
Sorry, just a quick comment. If you think about the transformer, like a GPT-style transformer, what it does is it takes an input set of words tokens of length L, and it outputs a sequence of length L. It just so happens that each one is the next token prediction, okay? But if you're wondering, like, how could I drop this in and replace, right? Basically, this is a unit that will ultimately do the same thing as a transformer. It'll take in a sequence and it'll output a sequence.
Diagram. And going in a little more detail, basically the first equation here can be thought of as taking your input U and expanding the dimension into a latent state X, following a simple linear ODE. In the control diagram, you view it as passing the input through some sort of feedback loop. And then this hidden state X then gets projected out to an output that has the same dimension as the input. So turning the diagram on its side gives the left part of this diagram. So at its core, we'll be parameterizing our model using these parameters A, B, C, and D. And this is implicitly a continuous time model. It defines a function-to-function map.
Sorry, one more editorial comment. You'll notice that he has D's in here, okay? And this D is not at all dependent on your hidden state. So at some point in one of the later papers or the S4 paper, whatever he says, the math of D is trivial, so we'll just stop talking about it from here on out. And then he just talks about A, B, and C for the rest of the paper.
And the machine learning term that he used is the skip connection, essentially some form of skip connection from the input to the output.
Yeah, but in case you notice, some places it says ABCD, and other places it only says ABC. The D is still conceptually still there. It's just it's not the tricky math part, and so they just stopped talking about it.
Continuous time model. It defines a function-to-function map. Now, you can to work on sequences instead of functions, we will need to convert this from continuous time to discrete time. And basically, the way this works is that there are certain well-studied formulas or transformations that can take your continuous time parameters A, B, C, D into discrete parameters A bar, B bar, C bar, D bar. They're basically just simple formulas of the original parameters. And then given these discrete parameters A bar, B bar, C bar, D bar, which I'll be denoting with blue in general, your continuous time model gets transformed from a differential equation into a recurrence. So now here we still have an input u. The input is still u and the state is still x, but instead of a differential equation, it follows a very simple linear recurrence that defines this hidden state. And then the hidden state gets projected back out to an output, y. So basically, the original state space model can get transformed into this linear recurrence that has very similar form, but using a slightly different representation, A bar, B bar, C bar, and D bar. And so the upshot is that the discrete version of the state space model is in fact a simple linear recurrence or a linear RNN. And in the diagram, basically what you can view this, you can take your original continuous time feedback loop and unroll it as a discrete recurrence in discrete time. And it looks exactly like an RNN. So you feed your inputs u in one at a time. And for each input, you update your hidden state and then project it out to an output. Now, the final view is the convolutional view. And the main idea here is that because it's a simple linear recurrence, you can actually unroll it in closed form. So here, remember again, the inputs are sequence u and the outputs are a sequence y. And it turns out you can just unroll this recurrence by hand and derive a closed formula for the output in terms of the input. And then by collecting certain coefficients into a representation that we call k bar, then it turns out that the entire output vector y is a simple convolution of the input vector u. And so this is actually the most important representation, and we'll see why later. But this is the way we usually train the model. And the main takeaway is that the whole state space model can sort of be viewed as a fancy convolution, where the convolution filter is the convolution filter k bar is parameterized in this special way using parameters a, b, c, d. And by the way, the d term was omitted here because it's kind of like a skip connection that is very easy to compute. And so in the diagram again, on the right side here, this is the convolutional view is depicted as just you take your parameters and you materialize this convolution filter, and then the entire output as a vector can be computed in a vectorized way with a single convolution. Okay, so these are the main
pause for 2 seconds?
State space model and how it relates to this.
So the way I'm kind of, can you correct me if I'm wrong? The way that I'm kind of thinking of this is essentially you're either rolling out the continuous time into a discretized, where you're compressing time by not computing it in a continuous fashion, or you compress all time essentially, and you look at everything all at once, which is the convolutional view. And that the convolution really, at least from what I can tell, if I were to use kind of an LLM approach, is one big attention view of the entire thing. That's the ultimate goal of the convolutional, is to take all of the other parameters of A, B, C, and D, and just say, here's how much I look at this piece of the input, and combining all of those computations that would have been rolled out over time into a single attention threshold. Much more complex than attention threshold because it's a vector, but essentially an attention threshold for each piece of the input all at once. Is that a decent summary?
I think maybe
That is
not
correct.
exactly that. You might like the way Yannick describes S4 in the video that we're going to get to next week, and his early description of Mamba. So the first part, if you look at A bar, okay, and you say, for example, x at time step k, I don't know why it's k instead of t, but whatever, at k versus time step k minus 1, you multiply by A bar. But A bar is the identity plus this delta A, okay? So that's going to be the identity times this, so it's just your old state plus delta A times your old state. Okay, so basically, yeah, it's just your old state plus, you know, whatever the change is. What he completely omits is all the gnarly math for how do you integrate this uh, equation, you know, x prime. Okay.
Yeah, I mean, the math is certainly going to be gnarly. I'm just trying to get to what's the goal of that? What's the end state? And I think the end state is either a compression as a function of shifting from continuous to discrete, or a compression by giving the totality of context all at one pass, essentially.
So I think the idea is that if you think of this continuous time function, okay, what we are actually storing, what we're literally storing in the computer is A, not A bar. Okay, we calculate A bar so that we can do the RNN activity, okay? But that means that the weight matrix, and he shows like the A weight matrix is this n by n, or whatever you decide your hidden size is, okay? So if your hidden latent is n dimensional, then it's this n by n matrix. And even when you have it initialized with some kind of random numbers or whatever, it is going to have all the dynamic properties of this continuous time function. If instead of storing A in your computer, you stored A bar, it would not have the continuous time dynamics. It would act like an RNN because you just have A bar. Great, I have an A bar. You need the fact that only certain A bars are possible because A bars are the functions of any possible A. That gets integrated into this. So that's what you inherit by having the first two steps, the continuous and the RNN. So I may not be saying it quite exactly mathematically rigorously, but I think the intuition is not all A bars are possible, or not all A bars are equally likely, because any A may be likely, but they will only turn into a certain limited subset of A bars that have these continuous time dynamics. So that's why you do this first part. Once you get an RNN, it is kind of trivial to just unroll it. If you unroll it L times, you're going to trivially get this. And so then that means that you can now parallelize the
into a single
exact
kernel.
same operations. It's the exact
Yeah,
same
I got you.
math
Okay,
if
cool,
you
cool.
did it iteratively.
I think I understand it then.
Isn't that because there are not nonlinearities in this model?
Yes, that's
you can't
exactly
roll it
right.
back. You can't kind of
only
unwind
do this.
it if it had nonlinearities like an LSTM or something, but in this case it doesn't, so you can't.
Exactly. It is just linear. There's no activation function. There's no nonlinear. It's just linear. And so then that's where you just get A to the power whatever when you multiply it whatever times. And so that's when later on, when we talk about Mamba, we're gonna be like, oh crap, we just broke that. We introduced a nonlinearity, and now we broke it, and the convolutional view is going to be gone.
Yeah.
And I'm sure Albert spent months, years trying to bring it back, and he failed. So then he just said, hey, Tree, you wrote Flash Attention. Help me speed up this thing so that I don't care the fact that it's actually computationally worse.
Ted, one other question. Is it the case, so convolution is easier for training, better for training, the recurrence is better for inference. So is it the case that what we're going to be learning is K-bar, and then we actually need to translate back into the A-bar space?
You need to learn A-bar and B-bar because you're going to use those at inference time, and you need to learn K-bar. You need to learn both. But when we're training, we don't use A-bar and B-bar at all. We use K-bar.
Yeah, okay. So you end up with K-bar, and then you can this equation will allow you to map back into A and B-bar and C and B-bar.
So when you do K-bar, you can kind of parallel compute the gradients across all the sequence elements at once instead of having to do it unrolling through time. But you get the exact same answer as if you did it one at a time unrolling through time.
Yeah, no, I get that. Yeah.
Cool. Not sure exactly where we got to.
Way using parameters A, B, C, D. And by the way, the D term was omitted here because it's kind of like a skip connection that is very easy to compute. And so in the diagram again, on the right side here, this is the convolutional view is depicted as just you take your parameters and you materialize this convolution filter, and then the entire output as a vector can be computed in a vectorized way with a single convolution. Okay, so these are the main properties of the state space model and how it relates to the three types of deep sequence models we saw before, the continuous time, recurrent, and convolutional models. It turns out that this gives it a lot of really nice properties, which we'll see later. But there's some critical challenges that make it this unusable out of the box. And so that'll be the subject of the next few slides. The first challenge is that I mentioned in the beginning that these model families all have problems with long-range dependencies. And that's a problem we haven't addressed yet. So it turns out that state space models, sort of being a special case of these things, also have problems with long-range dependencies. Very concretely, if we look at the state space equation, and in deep learning, we usually take the parameters and randomly initialize them, and then start learning them. We learn these A, B, C, and D parameters. But if you randomly initialize them, this A matrix is the most important parameter because it controls basically the state dynamics. But with a randomly initialized A matrix, this model basically doesn't work well at all. So on the simplest sequential MNIST benchmark, which we'll see later, which most sequence models are expected to do quite well on, at least usually you expect at least 90%. This model does really poorly. The second problem is that I mentioned that there's three representations of the state space model, and having the representations gives you nice properties, but actually computing the representations, although it's feasible, it's very slow. And so this ends up being a significant bottleneck that makes it difficult to train these models. In a little more detail, if we just look at this convolution filter K bar, you can see how the two problems arise, because this convolution filter involves powering up this A matrix. And when you power up the A matrix, it runs into the same vanishing gradients problem that I alluded to earlier. And secondly, by powering up this A matrix repeatedly, you're doing a lot of extra work to maintain this state. And here, the sequence length is denoted by L, the state size is denoted by N, and there is the obvious way of computing this has a large factor of N extra. We think of our state size in general will be on the order of 100 or so, and so this is significantly slower than what you want. It makes it basically unable to train if you use the naive way to compute this. So to get around this, the structured state space model uses some specific, adds some extra structure. So there's basically what we do is we require a specific formula. We require a specific formula for the A matrix, which is called it was introduced by some previous work of ours called the Hippo theory of memorization. And this specific formula looks like this, this formula down here. And this formula was arisen by solving some mathematical problems involving how to memorize a sequence. And what happens is that if you plug in this precise formula for A and B, then mathematically your state space will then be trying to memorize your input signal, which should give it the ability to address long dependencies. And so the first thing is that by incorporating this formula, our model is automatically able to address long dependencies. And secondly, because these matrices are highly structured, it also allows us to address the computational challenges. Because intuitively, the idea is that we just need to figure out how to compute this thing for this specific formula for A and B. And then this formula has a very precise form. It falls under certain classes of structured matrices, and we introduced some particular algorithms that allow this to be computed fast. Here's a very high-level sketch of the most recent algorithm we introduced, which is the one we use for the structured state space model. And basically, this allows you to reduce several polynomial factors in the runtime, and this makes it about as efficient as any other, as efficient as possible for a generic sequence model. So going back to the challenges, basically by using that special formula for A introduced before, this incorporating it into the state space model automatically solves both of the challenges. It basically goes from very bad performance to basically state of the art on a lot of data sets, and it reduces the computation time to make it about as efficient as the fastest competitive sequence models. So in overall, the S4 model consists of just that state space model with initialized to the Hippo matrix using a particular parameterization. And then in our experiments, all we do is we just stack them using a very simple repeated block in the same style as standard deep sequence models. So there's a normalization layer, like layer norm or batch norm. We use then the S4 layer, which was what I've been talking about, and then some position-wise linearities and non-linearities as well. And we've evaluated this model on a bunch of tasks across different data modalities and different tasks. Yeah, so these include images, text, audio, and time series. And I'll go through a couple of the most important experiments.
Hey, Ted.
First of all, on
if I'm the only one struggling with that, I'll take it offline, but I'm not quite understanding this concept of a random initialized A is 50%. I wasn't quite sure what they said, but yeah.
Yeah. No.
Is
so
A not what we're learning?
You know, I don't completely understand, to be honest, myself. Dave, I don't know if you understand S4 better than me, but it sounds like ultimately what he's saying is they didn't learn A, they hard-coded it to be this Hippo matrix that is derived from Legendre polynomials, and maybe they're learning the C, but they're not learning the A and the B.
They're not learning A, so A is of a particular form, and then they learn B, C, D. Okay.
Yeah, and D also, they don't do anything. I mean, it's just a skip connection. So it is just A, B, and C, and A is derived using those formulas, which they then further enhance in S4 from Hippo to S4. Yeah.
Okay, that helps. Thank you.
Yeah, and then I'm a little confused, but I think in Mamba we're going to start learning A again. We stop using the Hippo initialization, so not 100% certain, but we could see that in the code.
Hey Ted, in Mamba they have 6, not these 4, right? They have 6 of them then?
We'll get to it.
Okay.
But it's I don't remember it being that different from S4. The difference is that right now A is fixed, but it could have been learned, okay? But even if it were learned, once you're done training, then it's frozen, okay? In Mamba, what we're going to see is that A and, which ones? A, B, and delta are actually not just going to be fixed. You can have a small neural network that says, for each input, this is the A that I want. For each input, this is the B I want. For each input, this is the delta that I want. They're just going to do a matrix multiply, simple linear MLP. But so now you get to say, for each input, I'm going to do something different.
And since we're paused here, that K bar has L-1 terms in it. So if I'm training on 1,000,000, L is the sequence length, right?
It's L because this one is A to the 0th power.
Okay, so if I'm training on a sequence of 1 million, this is a really big k-bar.
It is. That's why you need the efficient way to compute the elements of k-bar.
Okay. Okay.
Yeah, and go ahead, Roger.
No, that I'm good.
Yeah, they in one of the talks on Hippo, they even showed a very small matrix, like 5x5 matrix, for some of the problem that they were trying to talk about for the uh, uh, in the online case, I guess. It's a long sequence, but online sequence. Uh, even with a very small matrix, hard-coded like the way they shown here with the formula or the derivation of that, which we don't talk about, they got really good performance with a very, very small size as well. Also, they mentioned that, I mean, for different resolutions, and I'm assuming resolutions of how you discretize, I guess, the sequences, even for different resolutions for which you did not create that original A, apparently it worked very fine, very well with that as well. So again, I have no clue of the math. I haven't looked at that, but listening to some of those talks, that's what they talked about.
Thanks.
Thank you.
Yeah, so we covered everything that we really wanted to cover. The rest of this talk, which if we had time, I was going to keep playing, is just him showing some results on some different problems. Okay, so I think given that we're just about at the top of the hour, we'll skip those. If you are interested in watching the last 9 minutes or whatever, where he just shares some results, if you want to grab the slides, it has the link to the video. And actually, that's also the video that was linked in the meetup. So you can use either of those to get the video, and you can look at some of the results. If you want to get a better like feel for what kinds of things, that it was able to solve. But the main thing was just to give, obviously not a perfect deep background, but just a sense for what these state space models are and this interesting business of you want continuous time dynamics, but you want fast training and fast inference, which you can't just use the continuous time form to get both of those things. You have to basically convert it to an RNN and convert it to a something else sequence model.
Yeah.
So if we pick up next week there, I think that'd be a good spot anyway, but I wouldn't mind watching that in advance, so I'm not asking quite as many questions. Dev has his hand up though.
Yeah, so there is, I don't know how many of you have followed this LLM space benchmarks. So while most of the benchmarks are around transformer-based LLMs, there's one in particular called, I think, RNKV, which essentially was leveraging some of this concept for the attention. And sometimes it would make in the top 10 and then drop off when, as I think Ted mentioned, many of the engineering came in optimizing transformer. So it's interesting that there was one lone person, more or less, who was advancing language models using somewhat along the same lines technique to use RNNs in the instead of the explicit KV based attention in the transformers. So that's we probably have not discussed this over here, but or maybe anywhere that I remember, but that has definitely someone was trying to work on that all along, and now it is becoming more popular overall.
Thanks. So quick peek. We watched only the first 6 minutes of Samuel's video. So we're actually going to watch the rest of it where he said, okay, that was just the background on long sequences, right? Then he actually says, so this is what Mamba is, and this is how it's different from S4. Okay. So he'll go through that. And then if we have time, we'll look at a second video. We'll look at Yannick Kilcher's video where he explains what Mamba is. And he also kind of starts talking about S4 a little bit. So both of them do spend half the time giving the background and then going in. But I inserted Albert's video so that hopefully you guys have a little bit deeper appreciation for what's going on with these structured state space models, why they might be a good challenger for long sequences, because they inherit these continuous time dynamics, but we have efficient ways of working with them. Yeah, raised hand.
Hi. Yeah, thank you. So I had one very fundamental, very basic question here. So when we talk about large language models, essentially we start by saying that we have this particular vocabulary, right? These are the tokens which we create. And, basically my point is everything is assumed as a discrete distribution. It is not assumed as a continuous one. And in this whole work, they are starting from saying that it is continuous. We need to convert it to discrete. What I'm not able to understand is why are they saying that it is continuous and we need to convert it to discrete? If I mean, in language it is done this way. I'm not very sure how it is done in videos or other or speech. But my point is that why is this a problem? Why can we not assume that we start from discrete distribution?
I don't think it's a distribution, right? It's the unit of time, right? Is it? Am I mistaken there, Ted?
I think you could start from discrete, but I think what happens is, and when I'm done, anybody else feel free to chime in. If you just say discrete and nothing else, okay, there's just not a whole lot of math to build on. So like, fine, it's discrete. So just go slap some components together and try and build a language model, right? By borrowing from continuous time, you get to borrow from control theory. You get to borrow from the fact that, I don't know this really well, but basically Legendre polynomials for like continuous functions, like you're familiar with like Fourier decomposition, right? So you can do a Legendre decomposition of any function, and the different polynomials form a basis that spans. So basically what they're saying is that, hey, these Legendre polynomials will represent any, depending on how many terms you use, right? You'll have a small error, just like a Taylor series or a Fourier series, right? You'll have a small error at the end. But if you expand it to n, Legendre polynomials, you can I can't think of the right word, but you can imitate any function, any sequence, any shape. Okay, so this is like a really cool ability to have, and so the first video included that because the LMU, when they built that, you could basically put any pattern in, and it could perfectly memorize that pattern to within the delta of its rounding error. Because it's not an infinite Legendre series. It's only, we only need 100 or whatever, right? But to within that rounding error, it'll perfectly memorize any sequence you give it. So this is like a really cool kind of property you might want to borrow from, versus just starting from scratch saying, hey, I've got a language sequence, let me just arbitrarily try to come up with an architecture that will work.
So
sorry, go ahead.
No, I was just going to say, so my thoughts were that, continuous control theory and discrete control theory are both fairly well developed. So I don't see that distinction as that important. I did notice that the examples that he used were all analog, right? The heart, the sound, the whatever. So I guess he was coming from that perspective, a continuous application, continuous time series application, and then moving into if we quantize it, then we can analyze it this way with the matrix multiplies, etc.
Yeah, but I wonder if for specifically for language models, they would also just use the convolution which they have done in this work, the convolution function they have designed in this work. If they would just
meaning explicitly, what's the advantage of discretizing versus just using a convolution? Is that kind of the right way to express your question?
Yeah, I mean, I'm just wondering that if you had the embeddings, or whatever, pre-trained vectors for the tokens, and if you could put that convolution function similar to what you do in CNN, but instead of the small window convolution, the convolution function which they're talking about in this particular lecture, then maybe Yeah. I'm just wondering, maybe that would have already helped quite a lot as compared to starting from, but maybe it doesn't address the other analog signals as pointed out by Roger, I guess.
Dave, you have your hand raised, but do you mind if I try to give a concrete example first? Okay.
Please go ahead.
So one of the things that we'll see coming up is that there's this thing that people have noticed by trying to dissect transformer language models. There's this behavior that's called an induction head. Okay. And so the gist of it is, if you see something like, these are not necessarily single tokens, but just if you forgive the imprecision, if you see Harry Potter, Harry Potter, Harry Potter, Harry Potter has been talked about a lot, and then you see the token Harry, there's a much, much higher probability the next word is Potter, even though just generically, if you didn't have any context, you might say that, I don't know, lots of things could come after Harry. Harry Truman, Harry whatever, okay? And so there's this induction head that basically looks and says, I see this pattern where Harry was followed by Potter, and I'm going to learn that pattern so that the next time I see Harry, I'm going to bump up the prediction of Potter significantly. Okay, so this is something that is mentioned in the Mamba paper, that they say, I want whatever model I build to be able to do this. And you don't directly get that from control theory or whatever, but you do get it if you're sort of inheriting from this idea that Legendre polynomials, whatever, that these things can memorize things they've seen in the past. I saw this pattern, Harry, then Potter. I'm going to memorize that. Now, when I see Harry again, if I can properly access that information that I've stored away, other things won't fire, but this thing's going to fire and say, whoa, I got something to say. I think the next word's Potter. Let's bump up the probability. So that's kind of a concrete example of some mechanics that you want your language model to have. I honestly can't say. I'm not a control theory person. I can't, I don't really know exactly how Chris Ray and Albert Gu came up with these state space models and why they think that this is the way to the future. But somebody did mention that, he's got these analog things that he's looked at, and in the real world, you have really long audio sequences. You have really long, EEG sequences and stuff. Somebody else can tell me, in discrete control theory, you may or may not have as many examples of super long sequences. And so maybe it's just the fact that those continuous ones are really long has forced those people to deal more with this problem than maybe the discrete people have dealt with.
Yeah, I just wanted to add to Roger's question about the dimensions in the examples that they selected. So even though I think in the Hippo paper, they applied it mostly for one dimension, when people confronted them about a multidimensional problem, they mentioned that they did experiments with applying that for each dimension without worrying about the correlation across the dimensions, and still got pretty good results. But I don't know how that translated in S4 later on. So, but I know for Hippo, that's what was the case.
Yeah, this is the paper Dave's talking about.
Oh, actually, even before that. So this one is the H3 paper. The original Hippo, which came even before S4, I think back in 2021 or something. But yeah, thanks. Yeah, this is also one of the key papers in the direction of leveraging or optimizing transformers attention. Yeah.
All right, guys, we're a little over time. Thanks for sticking around. I hope this is a pretty good stopping point in terms of not super deep, but some intuition around state space models, which will allow us to then next week talk about how does Mamba jump off from there. And then we can see some of the pretty impressive results. There's nothing else that people have built that had as good performance as Mamba on small problems. It's not that they had really great performance on small problems and then they just didn't scale to be as good as transformers. So fingers crossed, maybe this will actually work.
Yeah, and this is like a university work, right? So in many ways, their resources are limited. So 2.8 and 7 billion is what they mostly end up experimenting with. And which is also really amazing to see that on one hand is OpenAI with trillions of models and all the infrastructure they can throw behind it, and how universities from working on the core engineering problems and optimizing those, and those kind of circle back into those big machinery anyway, like flash attention and I'm assuming some of this work, whether independently discovered by OpenAI and not published, or if not, then they probably are actively looking at incorporating something like this in their models as well. So academia is getting important again in machine learning with the kind of work that is, especially I've seen from Stanford, and LMU came out from Waterloo, and then there was this Liquid network from MIT. I think all those are along similar lines.